சரி, ஓகே. கேக்குதுங்களா செந்தில்?
எஸ் சார், கேக்குதுங்க சார்.
ஓகே ஓகே.
A pleasant morning, everybody. Let me first welcome God Almighty, whose endless mercies, guiding light, always keep us in the right path. I welcome our honorable resource person, Dr. A.K. Abdul Hakim, Principal, Dr. V. Chamundeshwari. I respected Dr. Suresh Kumar, sir, Vice Principal. Head of the department, Dr. P. Vignesh Kumar. Respected participants, I welcome all for the webinar. I request our respected Vice Principal, Dr. Suresh Kumar, sir, to give welcome speech.
ஹலோ, ஹலோ.
Good morning, everyone. This is Dr. S. Suresh Kumar, Vice Principal, KGISL Institute of Technology, Coimbatore. On behalf of KGISL Institute of Technology, Coimbatore, I welcome you all for this 2 days national webinar on fluid dynamics organized by Department of Science and Technology, Science and Humanities of KG Kite. So distinguished speakers of this 2 days national webinar, Dr. A.K. Abdul Hakim, Associate Professor of Mathematics, Sri Ramakrishna Mission Vidyalaya College of Arts and Science, Coimbatore, and the tomorrow's speaker, Dr. G. Chandrasekhara from BMS College of Engineering, Bangalore, are going to be the resource persons for this 2 days webinar. I'm really happy to note that the Department of Science and Humanities is organizing this webinar on fluid dynamics, and also I'm happy that the 2 of the speakers are from the mathematics background. So on this note, I really welcome all the participants, the faculty members, research scholars, and student members for your active participation in this webinar today, as well as for the tomorrow's session. So the 2020 coronavirus COVID-19 pandemic has affected everyone in the world, with the ramifications in our public health, prosperity, and beyond. So there are so many lessons we can draw in the situation, but being a faculty fraternity, whether you are an engineering or an arts background, we have to think it in a different way. Like we have to focus on science and simulation on this particular context, and community and collaborations on the other hand too. For example, since it is organized and the speakers have a mathematics background, I just wanted to mention few things before I conclude. So I think we have to think about the simple mathematics in the scale of the exponential growth and epidemics turning into pandemics. How we calculate how the infections spreads, and it creates impact on each of the persons. So that where we use the simple mathematics for that. So we in the similar way, we have to think about how we can simulate it and how we can project the truth to the public, and also for the researchers is really a matter. So in there also the computational fluid dynamics also helps you in analyzing even the COVID situations. For example, when we say about a social distancing, how much is the distance we should maintain, also which involves the mathematics. So I think the COVID-19 is an infectious disease that spreads from person to person, mainly from droplets when an infected person coughs or sneezes. So the right distance is a function of the reach of the pathogen. So keeping that in mind, we can make the mathematical calculations, and we can contribute towards this the COVID time. And also the sneezing is not a simple phenomenon. It is a complicated phenomenon, particularly the experimentally, because I think the sneeze is a very complicated phenomenon with the multi-phase turbulent clouds, gaseous phase coupled with droplets, and a face mask can create the obstruction or redirection between the person sneezing and the person exposed. So we can take all these things into a simulation environment, and we can analyze and we can tell them the facts and figures. So I think in that particular aspect, though the fluid mechanics is from a physics background, but the applications varies from the applications have got a wide variety of the branch of engineering, mathematics, biomedical, or whatnot, the mechanical, civil engineering, and chemical engineering. And this is the right time to step into the analysis of the fluid dynamics. So I'm happy that the Department of Science and Humanities have taken up the right topic for the 2 days national webinar on fluid mechanics. So in this situation, I really thank the research persons, Dr. A.K. Abdul Kahim and Dr. G. Chandrasekhara, for accepting our invitation to enlighten us as well as the participants on the fluid mechanics topics. And also I welcome all the participants once again for sparing your valuable time even in this pandemic period. So I, on behalf of KGISL Institute of Technology, I welcome you again, and I congratulate the organizers for the successful conduct of this webinar. Thank you.
Thank you so much for a wonderful start, sir. So on today's session, we will be focusing on introduction of nanofluid and boundary layer flow. Now, I would like to introduce our resource person of the day, Dr. A.K. Abdul Hakim, Associate Professor of Mathematics, Sri Ramakrishna Mission Vidyalaya, College of Arts and Science, Coimbatore. To minimize the time, I would like to list out the main attributes of a His area of interest is His area of interest is partial differentiation equation differential equation, computational fluid dynamics, nanoboundary layer flows, heat and mass transfer, magnetohydrodynamics, entropy generation, and slip flow models, etc. His academic qualifications are PhD in Mathematics from Bharatiyar University, PGDCA and MPhil, MSc in Mathematics also from Bharatiyar University. His B.Ed Mathematics in Sri Ramakrishna Mission, Vidyalaya College of Education, and his BSc Mathematics in Vivekananda College, Gurukula Institute, Madurai. He also has 18 plus years of teaching experience. He is a guide for MPhil and PhD candidates. He has guided around 18 MPhil scholars and 6 PhD research scholars. He has been the chairman of question paper sitting at Periyar University and BOS members at various colleges. He holds in delivering many lectures and acted as a resource person at 40 plus different institutions. He has presented and participated in many conferences, symposium and seminars, etc. He has published around 60 journals. He is also a reviewer of many journals. Such a versatile personality we have today as our resource person. We are proud to have you, sir. Thank you for accepting our invitation.
Thank you, ma'am.
It's time to move on to the today's session. Over to Dr. Abdul Hakim, sir.
Thank you, ma'am. Good morning to one and all present here in this webinar session. First, I would like to thank the organizers, management, principal, vice principal, and organizers of KGSL who gave me this opportunity to share my knowledge, my ideas in introduction of nanofluids in a boundary layer flow. Before going to my talk, I would like to explain very briefly about the role of mathematics in our life. We can say without mathematics, the world is incomplete only. There is no doubt at all. So mathematics play a vital role in each and every part of the world. If you think our natural phenomena is a non-linear one, we can't predict anything in this world. It will be changeable only. So in this world, which one is permanent means change only permanent in this world. Thus, change is studied in our mathematics. That is nothing but our dy by dx. With respect to time, how the x is varying. So, such a wonder, the permanent things is studied by our mathematics. In that mathematics, we are having pure mathematics and applied mathematics. Now we are going to deal with, I am going to, the fluid dynamics is the one of the part of the applied mathematics. So now I am coming to my plan of presentation. So I am going, first I am going to give the basics of nanofluids, some basics ideas of boundary layer, and different types of fluid, nanofluid models where we are used in our research. So I am going to explain 2 or 3 problems in boundary layer flow in using nanofluids. So before going to our talk, we want to know how the fluid dynamics is used in our life. So that is very, very essential. Before going to start the fluid dynamics, just you want to know, I will recollect some ideas behind that. So mechanics, all of you know that it is the oldest physical science that deals with both stationary and moving bodies under the influence of force is called mechanics. In that mechanics, statics is there. It is a science which deals with the body at the rest is called statistics. Next, if you come dynamics. So what is meant by dynamics means it is a science which deals with the bodies in motion. It's called dynamics. So if you now coming to the fluid mechanics means The fluid mechanics is a science which deals with the behavior of the fluid at rest or in motion. So that is called fluid mechanics. So without fluid, we can't live in this world. So there's no doubt at all. Because we in and around, we are surrounded by the fluids only. We are breathing air. So that is also a fluid. So like that way, we can able to say the fluid dynamics play a vital role in the relevance of your day-to-day life. Our heart is pumping blood through the bodies and supplying the oxygen and nutrition to each part of the body. So that concept is basic on our fluid dynamics. So like that way, we can able to tell more and more problems in our life. The engineer environment in our house and offices is based on the fluid dynamics principle. So it is entirely different topic. So I won't go for that. So before going to the nanofluids, so what is meant by fluid we want to know. So what is meant by, before going to fluid means we want to know the states of matter. So matter is made up of molecules. So states of matter, we all of you know that the gas, liquids and solids are the three states of matter. In these three states, the gas and liquid, we will say it is a fluid. So why we are telling it is a fluid means the definition of fluid is the substance which is capable of flow is called fluid dynamics. If you see that the slide, you can able to see the coherent force between the two molecules in solid is very high when comparing to the liquid. If you compare the liquid with the gas, the molecule, the coherent force is very, very less. So that's why the gas are moving, so liquids are moving without any external force. So that's why the gas and liquids are the fluids. So that is the fluids. In that fluid, we can able to divide it into compressible and incompressible based on the properties of the fluid. The fluids are classified. So so classified as a compressible or incompressible, Newtonian or non-Newtonian, like that way we can able to classify. But nowadays, in the recent scenario, if you take means, the nanofluid play a vital role in both the engineers and in our day-to-day life when comparing to our ordinary fluid. So now I am going to my topic is going to majorly on the nanofluids only today. So what is meant by nanofluid? I already told that the air and liquids are the natural fluids. But nanofluid is not a natural fluid. It is an artificial fluid. It was first introduced by Choi in 1995 in his laboratory. So it is a new class of fluid containing some nanoparticles of the size 1 to 100 nanometers. So that we will say it is a nanofluid. So we want to think about the nanofluid means, so in the first we have some you take some liquid in your glass. You add some nanoparticles, then it will become a nanofluid. So this is the basics of nanofluid means in that base fluid, we can add some nanoparticles. Then if you mix means, then it will become nanofluids. It have lot and lots of advances are there. So we will see it in later. So measure of nanos in our life. So you can think, so atom is 0.1 nanometer. So these are some examples I am giving. So DNA is 2.5 nanometer. So our hair is nothing but 1 lakh nanometer, ant is like 5 million of nanometer, our tennis ball is 100 million of nanometer. So these are some examples measured in our life of nano. So now we want to think about the nanoparticle means very, very tiny one. So now I am going to tell if you want to do the research in nanofluids means you can do either the physics and chemistries are doing the research in experimentally, but as a mathematician we are doing analytical only. So analytically we are dealing with research in research. There are two steps, two methods are there for preparing of a nanofluid. The first one is the single step method. The second one is the two-step method. The first one is the single step method and second one is the two-step method. In the single step method, we will get the nanofluids within the single step. In double step method, first we want to segregate the nanoparticles, then we will take that base fluid and we will mix together and it will form. Suppose we want to do the research in fluid in the nanofluids means the experimental, if you do the experimental part means it will be very high in cost. For example, if you want to study the nanoparticle, that gold nanoparticle, want to study the advances of uses of the gold nanoparticle means. So nowadays you know that the rate of the gold is very, very high. So doing experimental is very costly. But if you are theoretically, if you using mathematical models, if you solve means you will get without any cost, we will get some basics idea about our research. So now I am going to tell about one-step method. So what is meant by one-step method? The producing of the nanoparticle and dispersal of the nanoparticles in the base fluid in a single step is called one-step method. Just you take the base fluid, just you can put some molecules, then you can stir well, then you will get the nanofluid. So this is the simplest way of making the nanofluids. This is the best for synthesizing a metallic nanofluids only. So in the one-step method, it is best for metallic nanofluids. So if you come to the second two-step method is that in the first step nanoparticles are synthesized, and in the second step we will dissolve or disperse into some liquid medium. So it is called the two-step method. First we want to first step, nanoparticles are synthesized separately. After synthesize, that nanoparticles taken, and it will be in second step that it will be added into the base fluid. So that is and that we will make some dispersal. So that is called a two-step method. So this is the experimental. Those who want to do the experimental, so these are the two methods are there. So mainly we will concentrate our research is only on analytical only. So there is advantages also there, disadvantages are there in both the methods when we are doing in experimental. There will be a cluster duration is is formed in the two-step method, because if you add more concentration means the cluster will be formed or the layer will be formed on the boundary. So that will also there. So now what is the purpose of preparing the nanofluids? Well, inspect of using the fluid, what is the purpose of we are using the nanofluid? That we want to think. So already the nanofluid is nothing but combination of base fluid plus some nanoparticles. So if the base fluid is there means the heat transfer will be, suppose you are doing the heat transfer, so it will take much time. So if the heat transfer want to high means what automatically the thermal conductivity of that liquid we want to be enhanced or increased. Then only the heat transfer will be occur. So in this aspect, the nanofluid will enhance the thermal conductivity of that fluid. So how? Now I am going to tell. If you take the engine oil, so engine oil will have the thermal conductivity of 0.0115. So if you, for example, if you are using the engine oil in your car or two-wheeler, so it want to reduce the heat from the piston. For example, you are in the engine oil means that the heat will be there. So it want to reduce that heat. So engine oil will take much time. So engine oil is a ordinary fluid I am telling about. So in that engine oil, if you add some nanoparticles, so what will happen means the time of the cooling is very high. So that is the examples of the nanofluids in our life. So nanofluid will enhance the thermal conductivity of the base fluid. For example, if you have the base fluid have the thermal conductivity low much, if you want to enhance the thermal conductivity means just you can add some nanoparticles, then this thermal conductivity will be increased. So this is a new class of fluid which will advance the heat transfer fluids in engineering problems. So you can see that the thermal conductivity of the metals, water also there, water, silicon, aluminum, the copper, silver, carbon. The carbon have the more high thermal conductivity. So what are the factor enhance the thermal conductivity of the nanofluids? So already we know that nanofluid is base fluid plus some nanoparticles. So the nanoparticles play a vital role. So we can't able to add more and more means that's all. So what are the factors that enhance the thermal conductivity of the nanofluid means? The first factor is nanoparticles volume fraction. That we will denote it as phi. So what is nanoparticle volume fraction? So that is nothing but we are adding some amount of nanoparticles in base fluid. If you add more and more means what will happen? It won't be dissolved. So there will be sedimentation will be fall in the bottom of that layer. For example, if you are preparing a tea or coffee, if you add sugar, stir well, so it will dissolve on that tea. If you add more and more sugar, what will happen? So after a few attempts, it won't be dissolved. So that volume, that sugar itself acts some barrier for the heat transfer flow. So that's why the volume fraction phi is very, very important for preparing of the nanoparticle. It will enhance if it is minimized. The second thing is nanoparticle material. So material, we are having the two types of material. One is metallic nanoparticles are there, then oxides nanoparticles are there. If you want to have a more velocity profile, you want to add oxides. If you want to have the more temperature profile, so you want to add metallic. So nanoparticle materials also will enhance the thermal conductivity of the. Now the base fluid. So I already told the water is a base fluid. We can use some ethyl alcohol. So engine oil also. So like that way, the fluid also will also enhance the thermal conductivity of the nanofluids. That base fluid I am talking about. Next, if you come in the nanoparticle size. So nanoparticle size is very, very, very important. If the nanoparticle size is high means, if the it will be, the conduction will be formed. So nanoparticle size and the nanoparticle shapes are very, very, very important. For example, you take a cup of milk, just add turmeric powder. What will happen if you stir well? It will mix with, so that is also a powder, also a nanoparticles only. Just you put and mix together. So the milk will become the yellow color. If you add a little amount of that turmeric powder means, it will be dissolved, it will be in yellow color. So there will be no sedimentation in the bottom. So because of that size, because of the powder will have little size. So particle size also will enhance if you have enhance the thermal conductivity of the nanofluid. So like that way the shape, spherical shapes is there, cylindrical shapes is there. So these are the 6 phenomena of the temperature also there. Okay, these are the 6 phenomena or factor that enhance the thermal conductivity of the nanofluids. So now I am going to show some nanoparticles, examples of some nanoparticles. So oxides are there, metals. So oxides means Al2O3, CuO3 like that wise. So metals. So PCMs are there. To come to the base fluid means water, ethyl alcohol, oil or other lubricant, biofluids. So these are the some examples of base fluid. So that are the some examples of nanoparticles. So you can able to see this graph. So nanofluid will have high heat capacity. The blue color line, you can say that the nanofluid behavior is, when you comparing to the pure fluid, it have more heat transfer rate. But if you closely look at that diagram or figure, you can observe that the pure fluid behavior is more near to that wall. That is in the 4 degrees centigrade, it will have high heat transfer temperature, heat capacity will be there. Why means, for example, if you take the ice cubes, just you can heat. So what will happen if you heat any fluid means what will happen? Automatically the density of the fluid will be less. But in the pure water, what will happen means, so it will be increased up to the 4 degrees centigrade. After that only it will be decreased. So that's why there is the peak is observed in that graph. Because why this peak is observed means in that 4 degrees centigrade, the molecules, that hydrogen bond is dissolved here. So that's why there will be a high peak is observed. So generally, if you think means the heat capacity is increased if you use the nanofluid. So now I'm going to tell some applications of nanofluids. In transportation problem, we are using that applications that industrial cooling. So cooling purpose is very, very important. Cooling application is nuclear system cooling. Space and defense also they are using nanoparticles. Cooling of microchips, medical applications. So these are some applications of nanofluids in our life. So you can see here. So solid particles means, all of you know that the solid, the heat transfer by the solid is by conduction. Heat transfer, the mode of heat transfer in liquid, both conduction and convection. More or less, only the convection will be there. So in the what nanofluid is nothing but liquid plus solid. So conduction plus convection, it will give the advanced heat transfer rate. So that is the thing. So nanofluid means it will give advanced heat transfer rate. So these are the, I mean, this you can able to see the engine oil. If you use the nanoparticle engine oil means energizer, nanoparticle means what will happen? It will save our fuel 21%. So that is the applications of nanofluids in our day-to-day life. If you use that fuel, nano engine oil means what will happen? It will increase up to 21% of our fuel savings will be there. So now I am coming to the sports. Nowadays, when the ball, tennis ball are preparing using the nano materials. So how, sir, you can able to ask? When we are in the childhood days, what we will do? Suppose you want to play a cricket in the ball, that is rubber ball. So if you play the cricket or if you play anything, if you play cricket, it will, suppose you are short quickly means it will be burst. So on that purpose, what in the childhood days, what we will do means, just we will take that before before playing, just we'll take that ball and we will put take the needles and we will put 2 or 3 holes there. If the holes is there means automatically if the ball bounce means if you are short means the air will be released on that hole, so the lifetime of the ball will be increased. So that is the thing we did in our childhood days. But for that purpose only, nowadays they are using some nanoparticles. So there will be some fluctuation. So if the balls are, in the tennis ball, they are, if you shot means, the ball will be automatically, it won't be burst very quickly. It won't be. So that is the applications in our sports. In defense, they are using, if you use some nanoparticles in our dresses or in our clothes, it won't absorb any liquid. So that also there. So in defense, they are using our nanoparticles for preparing of their coats and etc. So like that way, we can able to tell the applications of nanofluid in our day-to-day life. So now I told that the nanofluid play a vital role in medical application nowadays. So how means this is the drug delivery. In the nanomaterials are used in the drug delivery therapy also. So how I am going to explain here. For example, if you have some cancer in your hand, so those days what they want to do, or some cancer in your lungs or anything, just you want to do some operation, open heart surgery, or just you want to operate and you want to take that cancer cell outside. The cancer cell is nothing but unwanted cells formed in our body. If you use the nanoparticle, so how the medicines are using is just you know that if, for example, in our hand that cancer cell is there, in that particular hand, the particular area, we can inject that nanoparticles. It will go and deposit on the cancer cell. If you give some external force or external magnetic force, if you dissolve it, that automatically the cancer cell will be destroyed. Just I'm going to explain this video. So this is the cancer cell is there. So what is going to happen? So this is application of nanoparticles in medicine. Okay. So you can see here our human body. So the black is, these are some cancer cells. So this is our nanoparticles. So just you can inject, or if you give that nanoparticle means just it will go and coated on that cancer cells. So here in the stomach, the cancer is there. Just we are injecting the nanoparticles. So what will happen means just the particles are going inside our body and going, and it will go and deposited on the cancer cell itself. So this is how it is depositing there. So if you give some external force means automatically the cancer cell will be destroyed. So this is you can able to see. So in my hand, the cancer cell is there. Just I'm giving non-magnetic nanoparticles in that things. If you apply the external magnetic field in our hand or in the things means body surface is there. So if you remove that magnetic force suddenly, what will happen means the non-magnetic particles which are in the cancer cell will dissolve that our cancer cell. So this is nowadays without any operating or without anything we can take the treatment for cancer cell using our nanoparticles. So this is one of the applications of nanoparticles in medicine. So I already told that we are going to deal only about theoretical. We are not going for experimental research. When we want to do the theoretical, the physical properties of nanofluid, we want to know the physical properties of the nanofluid. The first one is the thermal conductivity of the nanofluid. It is depend on the particle volume fraction and the kinematic and thermal conductivity of the base fluid and the solid nanoparticles. So we are having two types of models on the thermal conductivity. The first one is the Maxwell model of thermal conductivity is given in the equation Knf equal to. It was first proposed by in 1873. So this is the one type of thermal conductivity of nanofluids. The second one is Hamilton crossed model of thermal conductivity. So this is given in this equation. So in this model, they define n, the safe factor n. N is nothing but 3 by psi they define. The psi is nothing but the ratio of surface area, ratio of the surface area of the equivalent sphere having the same volume fraction to the actual surface A of the nanosphere particle. So if you put the psi is equal to 1, n is equal to 3, the automatically the Hamilton cross models will be converted into Maxwell model. So normally we will use in our research Maxwell model only flow. It will act as some obstacle. For example, if you pour some water in a flow and pour some oil. Hello? So you can able
continue,
to
sir. Yes,
okay.
sir. Yes, sir. Please continue.
Okay. If your viscosity means if water will flow the long distance when comparing with the oil. So because of the viscosity. So like that way in the dynamic viscosity, we are having two models are there. The first model was done by Einstein model is given in. If the volume fraction is less than 1, we can use that Einstein model. Now, next one is the Brinkman model. It was introduced in 1952 itself. So normally we will, in our research, we are using the Brinkman models only for viscosity. So like that way, the density. So density of nanoparticle is defined. Rho nf is equal to 1 minus 5 into rho f plus 5 into rho s. So density, nanofluid is nothing but base fluid plus solid. So like that same thing only. If you are having the density of the nanofluid is nothing but base fluid density plus solid density. Some of the concentration will be there. The linear concentration 1 minus 5 will be there. So this density of the nanofluid is defined in that equation. If we take the specific heat capacity, Bigino in 2006 they introduced that rho Cp of Nf is equal to 1 minus 5 rho Cp of F fluid plus 5 of rho Cp of solid. So these are the specific heat capacity of the solid. So if you want to do the research in means you want to know some physical properties. The main is thermal conductivity, viscosity, density, specific heat capacity of that nanofluids. So this table shows that some applied formulation of nanofluid particles. So density is given, electric conductivity, thermal conductivity, heat capacity, kinematic viscosity, dynamic viscosity, and thermal conductivity. So these are some examples of some properties of nanofluids. So now we have doubt. Sir, in that we told that the nanofluid is nothing but in the base fluid just we are adding 1 nanoparticles. So it is possible to add 2 or more nanoparticles. Yes, it is possible. So now in the current scenario, the research are going on that area. So that we will say it is a hybrid nanofluid. That we will say it is a hybrid nanofluid. So hybrid nanofluid is nothing but adding more than one nanoparticles in the base fluid is called hybrid nanofluid. For example, in our day-to-day life, if you had spicy, for example, if you had biryani, means what we will do? If you want to digest quickly, means just we will take lemon juice with sweet. Somebody will like salt. In that lemon juice, we will add some salt. If you want to digest very quickly, means it is not comfortable, means just you want to have lemon juice with salt and sweet. That salt and sweet lemon juice is nothing but our hybrid nanofluid. In that sweet lemon juice is nothing but the nanofluid. If you use the salt also, that is a different types of particles are there. If you take sweet and salt lemon juice means, so that is nothing but our hybrid nanofluid. This is a example of hybrid nanofluid. So like that way, here also because if you nanofluids means the properties of the liquid is very, very important. Like that way also, that hybrid nanoparticles also having some basic properties. You can see in the slide, you can able to see the density of the nanoparticle is nothing but fluid plus solid. But in the hybrid, in this study, we are using 2 nanoparticles. So 2 nanoparticles is there, means definitely the concentration of the volume fraction of the first nanoparticle is denoted by 5.1. The volume fraction of the second nanoparticle is denoted by 5.2. So we are at 2 nanoparticle concentration. Using that relation, we want to define the density. So rho NF. Just in that slide, you have the HNF. H is nothing but hybrid nanofluid. So 1 minus 5.2, that's second concentration, into 1 minus 5.1 into rho F plus 5.1 into rho of S1 plus 5.2 of rho of S2. Like this way, we want to define the density of the hybrid nanofluid. Like that wise, we can define the heat capacity, viscosity, and thermal conductivity electricity of the hybrid nanofluids also. So those who want to do the research in the nanofluid means, first you want to know this property, which property we are going to use here. In this slide, you can see that the viscosity is nothing but brick band model. So many models also there. Okay. So that is depend on our things. So like this way, you can able to do so I gave some basics idea about nanofluids. Now we will come to the boundary layer. So what is meant by boundary layer? So we want to know the definition of the boundary layer. If you ask me means, just I will give the definition. The boundary layer is nothing but a locus of a point at which the velocity of the fluid particle at 99.9% of its free stream velocity is called boundary layer. So this is the definition of boundary layer. The boundary layer concept was first introduced by Prandtl in 1904 at the International Conference of Mathematics held at Germany. He did that experimentally, and he gave some layers also, laminar boundary layer, transit region, and the turbulent boundary layer, using the values of the Reynolds number. If the Reynolds number is equal to 5 into 10 to the 5 means above, that means we will tell that is the turbulent boundary layer. Below that is nothing but a laminar boundary layer. So that is called critical. We will in the critical Reynolds number we will tell. So now I'm going to explain what is meant by boundary layer flow. So boundary layer flow means, for example, you are having the flat plate. So solid is there. Here the solid is stationary. The fluid is moving parallel to the solid. Above the solid, the fluid is moving. The surface where the fluid and the solids are touching together, in that region, that is the boundary of the fluid will be there. I will explain you later. In that boundary value problem, first case, you are taking first case, the solid is stationary, the fluid is moving. That is did by Prandtl in the experimental. If you, another case is also there. For example, the solid is stationary, the fluid is moving. So that cases also will be there. So example for that second case is the moving of any automobiles. We can able to tell. If you take our two-wheeler or car, so in car, gearbox will be there. In that gearbox, we will have some oils. So if you change that gear, what will happen? Automatically, the automobiles will be moved here and there, up and down. But the fluid is in rest. So our building is there in our house. The air is blowing very fast. So our house is nothing but the stationary things. The wind blowing our house. So the fluid, because the air is also a fluid. So this is the second case. The third case, the fluid also will be moved. The solid particles will also move. So that is the third case. For example, for third case means the aeroplane. The aeroplane is flying. What will happen? The clouds also moving here and there. The air in the atmosphere also moving. That flight is also moving in the opposite direction. If we want to, the flight want to go fast means what we want to do? So automatically the solid is moving next direction. The wind is moving in opposite direction. We want to reduce that force. If you reduce that force, then the flight will go very far. The force between that things is called drag force. So we will tell that it is a drag force. For example, the bus is going in X direction. If you want to get down, while bus is going on that time you want to get down. So if you get down, opposite direction of the bus means definitely we will fall down. So we want to run few steps on the same direction of bus. On that time you can observe some force. Some force will be there. So that force is called our drag force. So like that way we can, so many things are there in boundary layer. In our research, we are going to deal with only the first part. We are keeping that the solid is stationary, the fluid is moving. This is experiment did by the Prandtl, the German fluid dynamics, did in 1904. So I'm going to tell, I'm going to explain. So I already told that the definition of the boundary layer is nothing but the locus of the point at which the velocity of the fluid particle at 99.9% of the free stream velocity. So we will tell. So otherwise we can able to learn the boundary line is a region in a flow field inside which the fluid flow with a high relative velocity. In that region, the fluid is moving with a high relative velocity. So that is also a other definition of boundary layer. If you ask general means, so boundary layer theory, what is meant by boundary layer? I told that is engineer part of it. If you think about generally, I'm going to tell one example. In general, the large crowds are there. For example, any temple festival or some Radha Yatra. You think about some Radha Yatra is there. You can go upper layer of that crowd. That is, you can stand any building, just you can watch that Radha Yatra. You can observe that some publics are moving very fastly. Some peoples are moving slowly. Some peoples are moving moderate. If you draw some imaginary line, those who are moving very fast, those who are moving very slow, those who are moving very fast. So if you draw that line means, so that is the boundary layer. In general, I'm telling about. So that is the boundary layer. So now I will go to explain here the boundary layer. The surface of object is here. The velocity, the fluid is moving parallel to the surface. So we are having two regions. One is called laminar region, another one is called turbulent region. That is separated by the critical Reynolds number. If you take that very first layer of the surface, the layer which is first layer, very first layer to the object and the fluid, on that layer, the velocity is at 0. The velocity is 0 at that surface. That we will say that is called no slip boundary condition. That is called no slip boundary condition. In the turbulent flow, the boundary layer is unsteady only. So now I'm going to explain here. You can see. Just I'm going to consider. So now I'm considering. I'm considering going to explain boundary layer by river. So normally the river, the banks are not in a straight path. It is maybe wavy. So river is there, means some obstacles will be there. Some rocks will be there. So some solid surface are in the center of the. So I am omitting all the things. What I am considering here is the bank of the river is always straight line we are taking. So we are having two banks of river that we will take X as Y axis. So X is nothing but the width, that diameter of that river. If you closely look at that stream in that river means, we can observe three types of flow is there. In the left wall side, the flow is different. In the middle stream, the center stream, the flow is different. And the right side also different. Now you can see the real river flow. In that real flow, the stream is moving in the center of the river only, center stream only. If you see both the bank of the river, then it will be very slow. Sometimes it will be a stationary point will be there. So now you come to our model. So the velocity, if you think that the velocity of the flow will be high at the center of the stream only. In the both sides, the left side and the right side, the velocity will be very low. So there will be some rotational velocity will also occur in the banks of the river. So boundary layer is nothing but the study of the flow near the wall, the both side you can able to see. So that is called boundary layer. Now I am going to explain. So definition of the boundary layer here. So if you, I already told 3 types of flow will be there. In the boundary side, the 2 boundary side, the 1 flow is there, and the middle stream is high. So how abdomen? Because of the force. Cohesive force, we will tell that is the cohesive force and adversive force. So what is meant by cohesive force? So I am going to explain. The cohesive force is nothing but the force between, the interaction force between the same molecule. In the center of the stream, we'll have only the water molecules only. The force between the same particles, we will say that is a cohesive force. If you think about the boundary, in that boundary we are having that solid space, solid surface is there, liquid fluid surface is there. So the surface is different. If the force between the 2 different surface, we will say adhesive force. If the boundary, the adhesive force and the adhesive force is 0 means there is no trouble for us. Now we can able to think. The war is in between China and India is there. If the relation between them that is same or 0 means there is no problem. So there is some disturbance will be there means there will be fight will become in between the 2 countries because of the boundary. Because there is 2 different countries. So like that way, so the 2 different surfaces there means that force is called adhesive force. So that is going to mainly see in our boundary layer flow. The cohesive and adhesive force are different for different fluids. For example, I am given here, if you take water, the adhesive force is very high when comparing to cohesive force. If you take HD, mercury, the mercury means more viscosity will be there. So here the cohesive force is high when you compare it to adhesive force. So cohesive and adhesive force it differ for different fluid. It is not equal for all the fluid. So like that in this force, the surface also, the surface is changed also, the cohesive and the adhesive force will be changed. For example, you take the glass, you pour some water. So what will happen? It will go very long, very high distance. Because the adhesive force is very less in the wavy surface. But in the glass, the adhesive force is very. So for studying that boundary layer, both the adhesive force and the coherence force is defined here. For the adhesive force, the fluid party for the surface will also depend. The adhesive force is depend on both the surface and both the liquid. It is not constant for all the liquid or all the surface. So if you want to study the boundary layer flow means we want to know the surface also, we want to consider surface also, fluid flow also. So now I am coming to the definition of boundary layer. So we are studying the first case, that is in our thing, the boundary that in our thing the solid is stationary. We are keeping that solid as our stationary things. The liquid is only moving. So now I am going to now you can see here. Now I am going to explain the boundary layer concept here. So first I am considering the free stream. I am just considering the free stream. We are taking that y-axis. The free stream velocity is u infinity. The flow is perpendicular to the y-axis. In that flow, just I am adding one surface, solid surface. So in the free stream, just I am adding the soil surface. You can see the video, the red color, the very first layer between the solid surface and the liquid. In that layer is called sticks to the solid surface. That is u is equal to velocity. That we will say that is the no slip boundary condition. The very first layer for the solid surface and the liquid surface, on that layer the velocity is 0. Then we will tell that condition is called no slip boundary condition. So I am taking one point here. Just it is u. Just I am taking the flow is in the u direction. Just taking y-axis. If you see that, if you increase, if you go go y-axis means the automatically the velocity of the fluid is gradually increasing. The velocity of the fluid is gradually increased from the solid surface if you go on the y-axis. If you see in the red color arrow is there, in that particular point, the velocity of the fluid is 99.9% of the free stream velocity will occur. And I am considering one single point. Now you consider the whole region. In that whole region, if you take the number of points means we will get the number of the number of some zone of 99.9% of free stream velocity will be there. Just you draw the locus of that point. So it will form one layer. So that is called the boundary layer. Now you come to the definition, what I told. Boundary layer is nothing but locus of the point at which the velocity of the fluid particle at 99.99% of the free stream velocity. So this is the definition of the boundary layer. Free stream is there. Just I am introducing some solid surface. The fluid is flowing on the solid surface. Very first layer to that fluid is called. On that point, the u is equal to 0. That is no slip boundary condition. We will tell. We will take one point. If you move the if you study the velocity in the upward y direction, means the velocity is always increasing. One particular zone you will get 99.9% of the free stream velocity for a single point. Now you take the whole region to draw the same procedure. So you will get the many points of that 99 point the free stream zone will be up here. So just you can draw the line. So if you draw the locus of that thing means you will get boundary layer. So that is the definition of boundary layer. So okay, a layer inside which the relative motion between the fluid particle may exist. We can able to tell. So if you think about the flow of the fluid outside the boundary layer, we will say sometimes it is a potential flow that is different. That is gamma equal to 0. The flow inside the boundary region. If you, for example, if you take the incompressible fluid, if the flow fluid over the solid surface is incompressible, inside the boundary layer, you can observe the rotational flow will be there. In the beyond, if you go to the river, you can able to see. Suppose if you throw the thermocol, means what will happen? It will be rotated. Some rotation will be there in the boundary. If you throw the thermocol in the center of the stream, it will flow very quickly. It will go. So in that boundary, there will be some rotations also will be there. So this is the definition of the boundary layer. That the boundary layer, we are having three types of boundary layer: velocity boundary layer, thermal boundary layer, concentration boundary layer. In which point that the velocity is 99% of the free steam. I'm just, the time is running up, I'm going to rush the definition. 99% of the free steam velocity means, then we will say that is the velocity boundary layer. The same thing also, 99% of the temperature is found is called thermal boundary layer. If you are adding concentration also, the 99% of the concentration found is called concentration boundary layer. The PR, Prandtl number, I all of you know the Prandtl number. The Prandtl number is nothing but viscous diffusion by thermal diffusion. That is nu by alpha. If PR is less than 1, then the PR equal to 1, the PR is greater than 1 we are defining. If the PR is greater than 1, then the thermal boundary layer is thinner than the velocity boundary layer. If the Prandtl number is less than 1 means the thermal boundary layer is thicker than the velocity boundary layer. So these are the 3 boundary layers. So just I am going to show one animation of boundary layer over a heated flat plate. So this is a CFD. We use this is an example. If you use the CFD means computational fluid. For example, it is a fluid software. In that fluid software, if you increase the Reynolds number, the boundary layer is increasing, decreasing. You can able to observe. We are fixing the Prandtl. So this I showed only the examples here. So if you want to do the research in nanofluids means experimentally we can do, mathematically we can do, computationally we can do. If you have experimentally means it is high cost, we can't able to do the research. As a mathematician, we want to do the only by the mathematical, either by the analytical method or computational method we can choose. So this is that analytical method we will get some exact solution using some limitation condition because our governing equations are non-linear one. Our governing equations are non-linear one. So now we will come for one application part here, direct applications of boundary layer. Here the extraction process of plastic. So here in this you can see that the 4 layers are there. One is called extraction layer, cooling layer, cooler and cutter. So the boundary layer, our research is only considered on the cooling layer only, that is water tank. If the, for example, just I am showing here, you can see here.
Continuously. Extrusion uses a dye.
So here the extraction process, in that hooper we are putting some plastics. So it is heated with high temperature. In the dye region, it will get some shape. So that that we want to cool quickly. For that shaped particle will be stretched through the water bath. So in the blue color is that is called water bath. Suppose this water bath is used ordinary fluid means the length of the water bath will be very high. If you use the nanoparticle means the size of the water bath will be reduced. So the experimental cost will be reduced if you use the nanofluids. This is one of the applications of our nanofluids. So now I am coming to the first model. Okay, Vigino model. Vigino model. In this model, we are going to study only the thermophorus and Brownian motion effect of the boundary layer flow of a nanofluid over a vertical plate. In this model, we did not consider the particular particles. Just we will concentrate only on the thermophorus effect and the Brownian motion effect only. This is the study incompressible laminar flow. The beta naught is observed here. The governing equations is giving you here. First one is a continuity equation, second momentum equation, third one is the energy equation, the fourth one is the concentration equation. So how much amount of nanoparticles are added, we can able to see here. So corresponding velocity u and v are given here. So already we know that the properties of nanoparticles. Phi is the Solin body fraction. The boundary conditions is given here. So we solved this problem either by the analytical, the governing equations. We are having 3 types of equations. That is a nonlinear partial differential equation with suitable boundary conditions. So if you want to solve means either by the analytical, after non-dimensioning, it will convert it into the if you use some similarity scalar transformation means the governing equations are converted into non-linear ordinary differential equation with transform boundary condition. You can able to solve analytically or numerically. That is depend on the. In the first problem we solved using homotropic analysis method. We solved here. So we using the homotropic analysis. I'm not going to more detail about that analytical the solution part of the boundary layer, because tomorrow my friend is going to handle that section, particularly on the spectral collocation method. So I'm going to tell only the results here. Okay, in this we are used. So you can able to see that the effect of magnetic parameter on the Prandtl number and the dimensionless velocity profile is given here. If the magnetic force is if the magnetic force is increase means the velocity is decreasing. If the Prandtl number is increasing means the automatically what will happen means the velocity is increasing. So main you can able to see that the effect of Borromean motion of the thermal parameter of the dimensional temperature profile is given here. If the Prandtl number is increasing means automatically the temperature profile is decreasing. So in this model, so due to lack of time, just I'm going to so in this model, what we do in this model, the Bigelow model, we have only concentration on thermophoresis effect and Brownian motion effect. Okay, in the second problem, you can also it's the same problem. Just in this model, we are particularly deal with some nanoparticles. We are considering a steady laminar two-dimensional slip flow over a stretching sheet. We are applying that base fluid as the water and nanoparticle as a silver. We are taking this. So governing equations is given. The second equation is momentum equation. In that momentum equation, the last term represents the external magnetic force is used here. In the third is the energy equation. In that energy equation, the last term, second term in the right hand side defines the velocity, the radiation, thermal radiation effect is studied here, and also the non-uniform heat source sink also studied here. So using that result, so these are the some physical properties of the nanofluid. We used here as the Brickman viscosity is used. The KNF, that is thermal conductivity, is used here. Is Maxwell model is used in our things. So introducing the non-dimensional variable, the governing equations are converted into 7 and 8 using the stream functions. So what is the role of the stream function is the stream function will reduce the unknowns. So flow pattern is studied analytically using the Human function. Just we are using some new variables. Just we are using the Human function. We will get some results. So what is the result mean? You can able to see the velocity profile is if you increase the magnetic force, the velocity is decreasing. If you increase the magnetic force, that temperature profile is increasing. So if you increase the concentration, volume fraction concentration, the velocity is decreasing, but the temperature is increasing. So you can able to see the why it is happen means if you increase more and more nanoparticles in our base fluid means automatically there will be a Brownian motion will be there in that particles. So automatically it will reduce the velocity of the flow. If the concentration is increased, automatically what will happen? The heat transfer will be very high. So that is the reason beyond this figure. So now if you can be able to see these are some results. So in this study, what we have concluded. So this is our one of our study only. So velocity distribution is very high. The temperature of nanofluid of velocity distribution for different things. The velocity is very high for the oxide when compared to the metal nanoparticle. Ag and copper are the metal nanoparticle. Metal TiO2 and Al2O3 are the oxides. Oxide nanoparticle. So in this result, we conclude that if you want to reduce that velocity, you can use the metallic nanoparticle. If you want to have the flow velocity will be high, means you use the oxide nanoparticle. But reverse trends is observed in the heat transfer rate. And also the second law, that is the I'm going like this way. I think the time is 11:20. So I will stop my things. Okay. So like this way, we can able to do the research in our nanofluids. So already I told that those who want to start the research in the nanofluid. So if you nanofluid means nanofluid nothing but base fluid plus nanoparticles. In that base fluid, you can able to take either the Newtonian base fluid or non-Newtonian base fluid. On the nanoparticle, you can take magnetic nanoparticle or non-magnetic nanoparticle, or you can take the metallic nanoparticle or non-metallic nanoparticle. We did some research in this. We published 5 to 6 papers in this field. So like that wise also. So like that wise also you can do the research in hybrid nanofluids also. One of my students is doing that hybrid nanofluid also. So these are my, I think the time is out. So these are the reference. Okay. So what I'm going to conclude here means, okay, the nanoparticle means the small particle will have high impact in our life. So that is my conclusion. Small particle will have high impact. Nowadays we are just now all of you in this lockdown period. So okay, be safe in your house for to reduce to make your health to increase your immunity power. Just you have cup of milk with some pepper powder. So the pepper, just you are using pepper powder, you can drink it daily. Definitely it will give some immunity power. So that milk is nothing but our nanofluid. Okay, so that nanoparticles. Okay, so thank you for your attention. Okay, thank you, Ananda.
Questions and the chat box.
Sir,
Oh,
thank you for your thorough introduction to nanofluids, sir. Hope the
Thank you.
participants also got benefited through the session. And we have a few questions
Okay, ma'am.
asked by the participants, sir.
Okay, ma'am.
So one participant have asked, can we use non-Newtonic fluids as a base fluid to create a nanofluid?
Yes, ma'am. In the third model, we did our study using the non-Newtonian fluid only. You can able to use. So if you go to the Google search, just you can type our name. So many papers will be you can be able to find. It is possible. You can do the research. Both the Newtonian fluid and non-Newtonian fluid can also use it for as a base fluid.
Okay, sir.
Okay. Next.
Next question
And,
it's in
one-
chat box.
Okay.
It's
Okay,
in
ma'am.
chat.
I think the time is not enough for taking 1 hour, so that's why I gave the basics ideas only. So if you have because those who are doing the research in the boundary layer, they don't know the definition of boundary layer itself. So that's why I concentrate on my talk will be those who are going to start their research. It will be very useful. Okay. Next. Sindhil sir.
Chat box la questions irukku sir.
Chat box la questions irukku.
Yes sir.
Okay, I will see them. How to go? So what are the questions there? I didn't get any.
Sir, the second question is,
Okay.
what would be the dominating force in case of magnetic nanoparticles in drug carriers?
If you add the nanoparticles with the Lorentz force will act. because the Lorentz force will is the force acting on that magnetic nanoparticle. Because the ordinary fluid is there, if you add some magnetic nanoparticles. Okay, wait, I will get that questions also. Okay. Question is there. Governing. I didn't get any.
Sir, the second question is,
Okay, ma'am.
what would be the dominating force in case of magnetic nanoparticles in truck carriers?
That Lorentz force only. The Lorentz force only. The nanoparticles with the Lorentz force will act. Because the Lorentz force will. I think something. The force acting on the magnetic nanoparticle. Because ordinary fruit is there. If you add some magnetic nanoparticle. Yes, ma'am. Then next question, ma'am.
Yeah, the next question is, sir, what is the future scope of nanoparticles and nanofluids across the world?
Across the world, if you already I told that in medicine we are using that medical field only. The research are going in nowadays to cure the cancer cell without any operation. So the research are going. So if it's okay means it is because we will tell general applications only here. We can't able to give particular application because we are using the mathematical models. We will give some basics ideas only.
Okay, sir.
Okay.
Next question, is it possible to use two-phase model for hybrid nanofluid problem?
Yeah, ma'am, it is possible for using the two-phase model because that base fluid itself, we can take two base fluid. Okay. Now the research are going on, 1 or 2 papers are published. We are not doing in that area. In literature, I came across the 1 or 2 papers are there in our internet source itself. It is possible. If you go through the search engine, they will get some basic papers beyond that. So 2 or 3 papers are there. I don't know that. Forgot the name of the author also. Yeah.
Sir, a participant have asked to suggest some books for nanofluid models.
So nanofluid models. Okay, I will tell you later, ma'am. You can ask another question, ma'am.
Which is most effective, Newtonian or non-Newtonian fluids?
This is more effective.
Newtonian or non-Newtonian fluids, sir?
So Newtonian only more effective, ma'am. In the third problem, I didn't show the results. We get that Newtonian fluid will have more effect when compared to the non-Newtonian. It is depend on the nanoparticles also. The role of nanoparticles is also there. If you add some nanoparticles, means sometime the non-Newtonian will have. For example, in our third model, we used magnetic and non-magnetic. In the non-magnetic case, the non-Newtonian will have more impact. Like that way, it is there. We can't able to depend on the base fluid. If you depend on the particle, if you change that particle, means the effect is different. Also, we can able to observe. We cannot able to tell correctly, ma'am. So beyond that, both the nanoparticles also play a vital role, and the particles also there. That is
Okay,
depend
sir.
upon the particles only. Yes, ma'am.
And one more question, sir. What
Okay,
would
ma'am.
be the dominating force in case of magnetic nanoparticles? Sorry, it is the same question.
The Lorentz force I told, ma'am.
Yes. And one participant have asked, can you provide homotopy analysis code for skin friction? Is it possible to give any suggestion related to it, sir?
If they have any question, personally they can mail me. So I will give some suggestions and I will give
Sure,
some
sir.
ideas, ma'am.
Yes, sir.
Okay.
Okay, sir. Thank you so much for clearing the queries also, sir.
Thank you, ma'am. Okay, ma'am.
Thank you again for accepting our invitation and joining us today, sir. Thank you so much, sir.
Thank you very much for all the participants and the management and the organizers who gave me this opportunity to share my things. Okay, be safe. Okay, வாழ்க வளமுடன். ஜெய் ஹிந்த்.